All right, today we're going to talk about these things called lazy sequences. Okay, before we talk about creating our own lazy sequences, let's try and understand what a lazy sequence is. And we'll start by looking at the range function. So I think I've used range a few times in the previous videos. A range is a group of sequential values that follow some pattern. So if I called range here and passed in the value 5, it would produce all the integers from 0 up to but not including that value. Okay. If I called range 10 to 20, that should give me all the integer values from 10 up to but not including 20. Here's a version of range that takes a starting value, an ending value, and a step value. So starting from 1, it's going to add this step value to get 3, 5, 7, again up to but not including that last value. There's a function also called repeat. So this says repeat 3 times the value 5. This works with integers and strings. So here we're saying repeat 4 times the string mark. Okay, so you see the output there, but just to prove to you that that is in fact what gets printed out when you run the code. Okay, so this is kind of cool that we have these built-in functions to do these things for us. But there's an even cooler function called iterate. The iterate function is an infinite repetition of a function on a value. Okay, so here's a function I wrote called add10, and this takes in a single value, and the add10 function will add 10 to that number and return it from the function. Now, the way iterate works is you pass it a function to call and an initial value. This initial value is going to be passed into the function, and then the resulting value is also going to be passed into this function, and that return value is going to be passed into the function, and this is going to iterate literally forever as long as the program is running. So you definitely do not want to hit the run button in this one. Okay, so let's put aside just for a moment the fact that we can't possibly store an infinite sequence in our very finite memory. Right? That's what the iterate function is trying to do, is produce this infinite sequence of numbers. Okay, so let's ignore that for a second. And turns out we can use this other function called take to extract from the beginning of a collection. Okay, this version is safe to call, safe to run. We still have our same add10, but now we're going to take the first 5 from this infinite sequence of values. Okay, when we print them out, we see, yeah, it really looks like we are calling add10. Starting with that first value. Then we pass it into the function and add 10 to it. That's how we get 10, and then 20, and then 30, and 40. So how do we deal with this infinite collection in our very finite memories? Turns out a sequence is a collection of values. We've known that for a while now. But not all sequences come fully loaded with those values inside. Some are considered lazy. Okay, so here's some code that calls that range function from 10 to 100, but then we only take the first 10 of those values, and then we're going to print those to the screen. The call to range, however, does not create all 90 values like you think it might. Instead, it creates this thing called a lazy sequence. And the lazy sequence produces values only as they're needed. In this case, we only ask for the first 10, and that's all the range is going to create. If you call the range function without parameters, it will create an infinite lazy sequence of all integers. Okay, so here I'm calling range, and I'm not saying where to start or where to end. This will just, in theory, generate this infinite sequence of integers starting at the value 0. Of course, since we're calling take 5, it's only going to grab the first 5. But if it were really creating an infinite number of integers, the program would never end. Okay, so we kind of know for a fact that that's not happening. Creating a lazy sequence takes almost no computing resources. A lazy sequence is really just a plan for generating a sequence that, in theory, could be carried on indefinitely to produce an infinite sequence. Even if an infinite sequence could be created and stored in memory, it would be incredibly inefficient to do so just to pull out the first 5 items or the first 10 items. Okay, they're called lazy sequences because only the bare minimum amount of work is done to create just enough of the values needed. Sometimes, but not often, it is good to be lazy. So when we ask a lazy sequence to start to implement its plan and create those values, we call this realizing the lazy sequence. And the primary implication of lazy sequences is that as long as you can come up with a plan to generate values, you don't need to store large collections of values in memory. In other words, you only pay for what you use. Now, as long as there is a reference to a lazy sequence, it will cache values so that the second time you ask for the first 5 or the first 10, it doesn't have to compute them again. In that sense, a lazy sequence is a sequence. It can hold on to previous values. Once you lose the last reference to the lazy sequence, however, the cached values will be gone because of garbage collection. And if you want those values again, you're going to have to go through all the work to recreate them a second time. Okay, so here's some code that I'm trying to prove to you that, or show you how the values are actually cached. So I'm calling this function cache example. It takes no parameters. The first thing I do in there is create a let, which I'm basically creating this binding. I'm saying we're going to have this thing called first 5, and it's going to hold the first 5 from the range of 10 to 100. Okay, so the let begins here and it ends there. That means first 5 has basically a scope from this point to this point. So here I'm going to print the first 5. They should all show up on a line. And then here doSequence basically allows you to iterate through a sequence and perform some action. It's usually a side effect on a sequence. Okay, so this should print all the first 5 on a line, and then this is going to print each one of those values on its own line. Okay, but then the let ends. Okay, and then first 5 kind of falls out of scope, and what that means is there are no more references pointing to that the first 5 of the range of values here, or that lazy sequence. So now if we wanted to print those 5 again, here we'd have to re-realize them. Okay, so when we wanted to use first 5 a second time here, we use the cached values. But now, since we're outside of that scope, if we want the first 5 again, we have to do all of the work to recreate them. Okay, so you see those are the print line, then the doSequence is here, and then this print line, since it's outside the scope of the let, we had to go through all the work to generate those values again. And I'll show you an example later that actually proves how that caching works. Okay, now let's talk about how we can create our own lazy sequences. So a lazy sequence is this representation of a possibly infinite sequence. It only calculates its values, though, when somebody asks for it. One way to think of a lazy sequence is that it's a bit of code that continually adds a new value to an existing sequence and then supplies a plan on how to add the next value to the sequence if it's in fact needed. The plan is usually a recursive call to the function that is generating it. And I'll show an example in a second. So if you look at the built-in closure range function, it has the following overloads. So this one returns all integers. This one, all the integers up to the end. This one has a start and end point. This one has a start and end and a step value. Okay, what the built-in range functions don't have is this ability to say, I want to put a starting value, and I want the starting value to go infinitely on forever. Okay, so that one doesn't exist. That's the function I'm going to write. So I'm gonna write a function called range from that takes a starting value and returns an infinite lazy sequence of values from the past and starting point until infinity. Okay, so here's my function to create a lazy sequence. It's a function called range from, okay, and we pass in a starting value. Now there's usually 3 steps whenever we're creating a lazy sequence, so I put each step on its own line. The first is we are specifically creating this lazy sequence, and there's a helper to do that for us. And the lazy sequence, it's a sequence, but it starts out empty. Okay. The next thing we usually do is we do a const. Okay, remember what const means. We want to add something, in this case the start value, to another sequence. Okay. And this third line here, this is the plan for generating the next value. Okay. What it is it's a recursive call right back to the range from function, but this time we're adding 1 to that starting value. Okay. So we're doing a const, we're adding this value to this also. This is also a lazy sequence. Okay. Now I'm going to call my range from function. I'm going to start with the value 10, and I want to take the first 5. So that should give me, these are the first 5 values. There's also a function called nth, where you pass it a sequence, and it will go grab the 0-based index from that sequence. So we have 0, 1, 2, 3. So 13 is the value with the index of 3. Okay, and that's what we get here in the output. Now let's create the Fibonacci sequence. Okay, so we're creating a function called fib, and we're passing current and next. Okay, so when I call fib down here, I'm going to always pass in the starting values 0 and 1, and then I want to take the first 5. Right, so we know the first 5 Fibonacci numbers, 0, 1, 1, 2, and 3. Okay, so let's take a look at this function. Step 1, we're creating a lazy sequence. Okay. Step 2, we're consting the current value, the first value, to the lazy sequence. Step 3 is we come up with a plan, and the plan is to recursively call fib, which again is going to generate a new lazy sequence. But this time, our current value, we're going to slide the values over, so what was next is now going to be the current value, and the next value, the second parameter here, we're going to generate by adding the current and the next value together. Okay, and like we saw, this seems to work. I could take the first 15 Fibonacci numbers, okay, or the first 150 Fibonacci numbers. Oh, that might be a little too big, so we had an arithmetic overflow. Oh, let's say the first 75 Fibonacci numbers. Okay, so the numbers start to get very, very large very, very quickly. Okay, let's try and examine exactly what's happening here. So in the very first call to fib, we're passing in 0 and 1. That's current and next. So what we say is we want to take this lazy sequence value and we want to grab the current. We want to const the current value, which is 0, into the lazy sequence. So it holds the value 0. And then our plan is to take the next value, 1, and the sum of these two values, which also happens to be 1. And that's our plan for generating the next value. If somebody asks for that second value, well, now we're gonna call fib, passing in 1, 1. That was the plan last time. Again, we're going to take the current value of 1 and stick that. We're going to const that onto the lazy sequence. And then our plan is going to be to take the next value of 1. That's going to be the current. And then sum these two together to get 2. Okay, and we're going to repeat this process, grab the next current, come up with a plan. This is the next and the sum of current and next. Okay, and what we see here is we get the sequence. So for the first 5 Fibonacci numbers, at the end our lazy sequence held these 5 values, and the plan to generate the next one looks like this. Okay, so here's a graphical representation of what's happening. First of all, when we call that const function, it produces a const object. A const is a real thing. And a const has 2 data members, a first and a rest. Okay? And when you const something, the first parameter is a value that you want to add to the sequence. So here, when we do our const, we're adding a value and then basically a pointer to a lazy sequence or a plan to generate the next value. Okay, so the very first time we called fib with 0 and 1, we took the current value 0 and we const it. Okay, so that means the value here got stored, and then the rest was basically a plan on how to generate the next value. So fib, remember, returns this lazy sequence. Okay, and this is basically a pointer to it. So now when we take the second value, right, we const that 1 and come up with a plan to get the third value. And then when we take the next one, we const that value of 1 and come up with a plan for the next value. So then we const the value 2 and come up with a plan for the next. Okay, and so on. So we grab the third value, and when we did the take 5, this is what our lazy sequence looks like. So it is a sequence. It is kind of this list of values, and the last element in the list, it has a value of 3 and then a plan to generate the 6th value if we were to ask for that 6th value. Okay, it turns out not all lazy sequences have to be infinite. When you return nil from a function that generates a lazy sequence, it will not produce any more values. Okay, so here's a different version of myRange that takes a first and a past end point. This is basically how the built-in range works. But it creates a lazy sequence. Okay, but now we're going to do one of 2 things. Either return nil from the function if the value that gets passed in happens to be equal to the past end value. Okay, we're going to return nil. If that's not true, though, we're going to do what we did before. We're going to const the first value and then recursively call myRange. We're going to increment the first value and then pass in the same old past end value. And when I run this, you'll see it. This function does not create an infinite lazy sequence, because here I told it to stop basically when it got to 9, and here I told it to stop when it got to 110. Okay, so here's a different set of code. Before I said I was going to show you some code to prove that lazy sequences actually do cache their values. And I'm going to prove that by adding a side effect to the range from function that I wrote earlier. Okay, so this is one that takes just a starting value. It creates a lazy sequence, and then here's the side effect. I'm just going to print out the start value, or the value that gets const to the lazy sequence. Then everything else is just the same. So I const the start, and I recursively call the range from function, and I add 1 to the start. Okay, so down here I'm creating a def called myRange. Okay, and at this point you shouldn't see any prints at all. Let me comment out everything else in this program, just to prove to you that when you create a lazy sequence, it actually takes no resources. Nothing gets executed until you realize it. Okay, so if we had actually realized anything, we would have seen something get printed, but we didn't. So this proves to me that just creating a lazy sequence doesn't take any computing resources. Okay. Now do all is going to force it's going to force the program to realize the lazy sequence. Okay, so what I'm going to do is I'm going to take the first 5 from my range. Okay, so that should generate those first 5 values. Then I'm going to print a line, and I'm going to do all again. This time I'm going to take 10 from my range. By this time, though, the first 5 should have already been created and added to the lazy sequence. We're only going to see the prints for 10 through 14, since the first 5 have already been created. Okay, so let me run this. Okay, so when we said do all, take 5 from my range, as the side effect we saw the current values being printed out here. I asked to take 10 from my range, and notice we don't see all 10 values being printed because the first 5 have been cached. They've been added to that sequence, and the first 5 kind of came for free. Only when we needed the 6th through 10th elements did we actually have to go through and apply that plan to generate the next values. Because we stored a reference to the lazy sequence, the previous values are cached. Lazy sequences do take up memory resources when we keep a reference to the entire sequence, like we did in this example. Okay, we had a def called myRange. Okay, and that was basically a pointer to this lazy sequence. However, the programmer chooses how much memory to use by specifying how many elements to traverse. They only take up the resources when they're realized. A lazy sequence by itself is a sequence with past calculations being stored in the sequence and a stand-in for some future calculations, okay, or the plan. And the stand-in doesn't take up many resources at all. It's just a reference to another lazy sequence. Now, if we don't store a reference to the lazy sequence, then the previously generated values can be garbage collected to conserve memory. Okay, so let's look at this code here. This says, take the first 100,000 values from the range and print them. Okay. In fact, we can execute this. It's going to generate a lot of numbers. So it should be the first 100,000 numbers starting from 0. So the values at the beginning of the lazy sequence can be garbage collected after they've been printed. There is no reference holding the head of the lazy sequence. So any object that doesn't have a reference pointing to it can be garbage collected. Okay, so you can kind of think of this like a headless linked list. Okay, we generated all those numbers, but without a pointer pointing to the first element, right? And if no other pointers are pointing to it, these objects can start to be marked for garbage collection after they've been printed. So after they're printed, nobody else has a reference to them. They could start to be garbage collected as we're iterating through the sequence. Now the nth function makes this even more clear. With nth, we're only asking for a certain value somewhere inside the lazy sequence. Okay, so in this code here, we're creating a range from 10 to 20, but we're only asking for the nth value, the third value, and we're going to store a reference to that called third, basically. Now, of course, range produces a lazy sequence, so we only needed to generate 4 values to get to the one with the index value of 3. Okay, and 10, 11, and 12, they can be marked for garbage collection after we've grabbed the third. Okay, it's actually the 4th element, but the index with the value 3. Here we have a reference pointing to this one, but there's really nothing pointing to these other guys, and they can be marked for garbage collection almost immediately. Okay, and this means that we can really efficiently choose to not store all the values in a lazy sequence if we know we're not going to use them. Or if we think we are going to use them, we could store that cached value and we won't have to regenerate them each and every time we want them. Okay, so that's the basics of a lazy sequence. Again, it's usually a three-step process where you say you want a lazy sequence, you const a value to the lazy sequence, and then you have this recursive function call or plan to generate the next value. And that's pretty much how all lazy sequences are created.